To demonstrate this, let's look at a fairly straightforward example. So let's say we have a glider descending on a given flight path. This would be the flight path of the glider. This is of course the local horizontal, and between them is the flight path angle. So your glider would be right here. And essentially we have the same forces acting on it as we did before. So we're gonna have gravitational acceleration acting in the so here, let's say here we have the center of gravity, here we have the local vertical, meaning the ZE angle, and we have the local horizontal, which is the XE coordinate, and we have also the longitudinal axis of the aircraft and the vertical axis of the aircraft, right? And in the local vertical we have the gravitational acceleration acting like this. Okay, so if the aircraft has gravitational acceleration and it has a given mass, of course we're going to have the weight of the aircraft acting in the Earth's vertical right here, and because we have the relative undisturbed airflow, so let's say the V0, we're going to have a given amount of lift generated perpendicular to this relative airflow's direction, so exactly in the negative vertical axis of the aircraft. Let's say this is L0, and we have the amount of drag generated, which is D0. And this would, of course, both be L0. So L0 is basically CD times half of the density times the surface area times the V0. And essentially the drag 0 is the, here I have the, of course, lift coefficient, and here I have the drag coefficient, half of the density surface times the V0. Right, and we're gonna break the weight here into two components by the already known methods. So here we're gonna have the flight path angle. So here we'll have the weight times the cosine of gamma, and here we'll have, let's say this is V0, and here we'll have the V0 times the sine of gamma. Okay, this is essentially W0. Okay, so what happens if I increase the mass of the aircraft from M0 to M1? So of course gravitational acceleration remains the same, but essentially you're going to have a larger mass right here, right? So W1, which gonna mean a larger vertical component, so the V1 times the cos gamma, because the gamma is unchanged for the moment, this is just simply going to be larger, and we're going to have a larger W1 times the sine of gamma, right? And so to counteract this in the vertical axis, we're going to be needing to generate a larger amount of lift, right? So essentially right here we're going to have L1. And how can we generate more lift if the lift coefficient is unchanged? Of course, we're going to have to increase the speed to V1, right? So let's use a different color for it. So to, I don't know, to V1. And essentially this V1 has to be larger than this V0. right? So this v1, let's say is right here, is going to be a larger velocity. So essentially, if the lift is going to be larger, in that case, the drag with the increased speed is also going to be larger because you have the drag coefficient, have the density, surface area, which have not changed, and times the v1, essentially the drag is also going to be larger, right? Right here. So the drag 1 is going to be larger than the drag 0. So therefore we can see that by this interplay of forces generated during the glide, we can definitely see that because of the increased mass, we can maintain the same flight path angle by increasing the lift with the increase of the speed, which then again leads to an increase of drag, but this increase of drag is basically counteracted by the increased weight apparent thrust. Right, so therefore the forces, the sum of the forces remain in balance, and altogether is still a zero vector, and altogether we can see that the acceleration is going to be 0, the sum of the acceleration is going to be 0, and the flight path angle essentially remains the same, right? So I think this way it's even clearer that for a given flight path angle, the mass has no effect. So let's look, however, at something else, the effect of configuration on the flight path angle. So the effect of configuration on the flight path angle. Again, the flight path angle, tangent gamma, we said is going to be a function of the CDCL, right? So the drag to lift, or the drag coefficient to lift coefficient ratio. So to understand the effect of configuration, so for example, extending the flaps, so for growing from a clean configuration to flaps, we need to plot the polar curve of the airplane. Okay. So if you guys can hear the horrible music in the background, apologies for that, that's just coming from the neighbor. Okay, so just before you judge my taste in music. Okay, so here we have, just like in the previous case, a polar curve for the clean configuration, right? So this is a general polar curve, but it is for clean configuration. And we saw that the optimum flight path angle would occur exactly in the tangent, right? So right here. So this is the gamma min, let's say gamma clean min. Right, so the minimum flight path angle for the clean configuration, so the minimum amount of drag to lift ratio. So what happens with the entire curve if you extend the flaps? Well, first and foremost, the CL max increases. So your CL max for the clean is approximately right here. So your CL max clean, like it increases, like CL max flaps, but also your drag is going to also increase, right? So your CD is also going to increase with the flaps, the CD0, and what you can see all together is that the whole curve is going to move up and to the right, so it's going to look something similar to this one. So it looks like this with the flaps, right? And so let's look at the effect on the flight path angle. So if we just want to compare the minimum amount of flight path angle that we can achieve in both cases, we can see that the gamma flap min, so the gamma flap min is larger than the flight path angle, the optimum flight path angle with the clean configuration. So therefore, from this one we can conclude that the CDCL, so the CD flap over CL flap optimum is going to be larger than the CD clean over CL clean. CL clean, right? And so from this, what we can conclude, well, we could have also directly concluded it from this one, is that the tangent for the gamma in case of the flap is going to be larger than the tangent of the gamma in case of the clean configuration. So what that essentially means, so this is the clean one, right? So what that essentially means is that your flight path angle is going to increase no matter what if you use if you're using configuration, right? And so what that means is that let's take a fairly straightforward example. So here you have the airport, or field, for example, and here you have the runway on the airport. So here's your runway right here, and initially from a given altitude, which is, let's say, right here, is you're starting the glide from, let's say, this point. And so initially your flight path angle is the following. Let's say is the gamma clean, right? So this is the clean flight path angle. Let's say you're continuously flying on the optimum speed, so the best glide speed in each case. Okay, so you see that you're going to be too long because your flight path is going to touch down approximately halfway down the runway. So that's not really good because your landing run is going to be relatively short, right? And that's also dangerous. It's not always good to be long. It's almost never good to be too long. Of course, from energy management point of view, you still have more options then compared to the situation when you're too short, but we're talking about a good optimum flight management. So what you can do at this point, right here, let's say, you can extend the flaps. So extending flaps right here, extending flaps, and what it does to your initial flight path angle at this point, so let's say you're at this pressure altitude or this height. So this was your, actually instead of using the dotted lines, I'll just pull straight. So let's say you're opening flaps at, this position. Okay, so this is your initial flight path angle, the gamma clean. But as we said before, as we saw in the polar curve, your flight path angle when flying with the optimum is going to increase, right? So your flight path angle is going to increase to an extent, and it's quite possible that, depending on the effect of flaps on the given aeroplane, or on the given type of airplane, which of course depends on the size of the flaps and the aerodynamic properties of the wing and of the aircraft altogether, and of course by the amount of flaps that you extend, because of course extending one notch of flap compared to a full flap extension is of course very significant. But let's say you extended full flaps, and now this is your new flight path angle with the flaps, and so you can see that altogether, you're going to be aiming, your flight path is going to be aiming approximately at the threshold of the runway. So you have all this distance to bring the aircraft to a complete stop, right? But this also entails that if you open the flaps prematurely, so if you open the flaps at this point, you're going to increase your flight path angle quite substantially, or by the same amount. So these two essentially would be parallel to each other, right? And altogether, you can see that if you extend the flaps prematurely and you achieve this flight path angle, you're going to come short, because here's the threshold and you're going to touch down right here. So in this case, you're going to be coming too short. So it's a very crucial part of your training to understand during the flight training exactly when to open the flaps. And this will come mostly with experience, to understand when to open the flaps, and judging with your side, basically, whether you're high or whether you're low. But to understand this phenomena, how extending the flap changes the flight path angle, is very, very crucial, right? Because if you don't, in that case, you won't really understand why you're opening flaps, too late or too early, and how can flaps alter your flight path initially. Because until you don't get the experience to judge an optimum flaps opening point, until that case, the only thing you can rely on is your knowledge on the subject, on how the flap basically alters the flight path, and how all these basically factors affect the flight path of the aircraft, right? So we saw that it's actually beneficial during an emergency to open the flaps, because it can alter your flight path angle, and if you were too long, and if you open it at the optimum time, it's going to affect your flight path angle in such a way that you can achieve your optimum touchdown point. However, if you open it too prematurely, you can end up very short, right? So this is the sort of caveat in this whole sort of discussion. Okay, and with regards to the speed which you need to maintain if you open the flaps, we need to sort of draw the power required curve of the aircraft, right? Because essentially the drag curve of the aircraft, of course. So we're going to examine how the configuration affects the drag curves and essentially the VMD, right? Because we agreed that we need to maintain the VMD to get the best range, the best gliding range, right? So here we have the clean drag curve, and here we have the VMD clean, right? And so what happens with the aircraft when you deploy the flaps? We already know at this point, so the whole drag curve is gonna move up, and it's gonna move to the left as well. So it's gonna move like this. So this would be the flaps and gear drag curve, right? And so what we see is what we already knew, is that the VMD flaps is gonna be less than the VMD in clean configuration. So altogether, we need to maintain a lower speed after deploying the flaps to get the optimum amount of flight path angle, but that's also visible from the polar curve of the aircraft. But we got the same result basically here. So to get the optimum flight path angle, which is larger, so essentially, and this is why it's interesting, so you're going to be maintaining a larger flight path angle with a lower speed, essentially, right? And so that's the effect of configuration. So anytime you have configuration during the descent as well, or during the glide, is going to increase basically your flight path angle. Okay, so let's talk a little bit about the effect of the wind. So the effect of the wind is basically the same as we had during the climb, and however for the gliding is going to be a bit different. So if you think about it, so the effect of wind. So if you remember from our previous discussions regarding the climb and how it changed the flight path angle during the climb, it's going to be the same effect essentially. So we're going to start from right here, and if we have a still air condition, let's say this is going to be our flight path angle and still air condition. So we begin from here, right? And we begin right here. Here we have our glider, and this is like the gamma no wind or still air flight path angle. Okay, so how do you presume a headwind is going to change the gameplay? Well, it's fairly simple. Just like in the case of the climb, when it increased the flight path angle, it's going to have a similar effect right here. So essentially, we're going to be at every single point, compared to the ground, of course, every single point, this headwind is gonna push us back, so to speak, and this whole effect is going to be added up throughout all this flight path, and essentially what this leads to is an increased flight path angle, right? So this flight path angle is much larger, or larger essentially than the no wind case. So the gamma headwind is, and that's best visible here, headwind is larger than the no wind scenario. And so what's the case if you have let's choose another color. What's the scenario if we have a tailwind? Well, if we have a tailwind, in that case, just like in the case of the climb, the flight path is going to be shallower, right? Because compared to the still air condition, every time the tailwind is going to push us further in the direction of the movement, and throughout all this vertical distance during the glide is going to add up along our glide. So what that essentially means is that the gamma tailwind is going to be shallower than the other ones. And I think down here it's not that visible because the difference between them is not so great, but up here, you know, it's essentially very visible that the gamma tailwind, you know, is the most shallow, and the gamma no wind is somewhere in the middle. So, you know, actually that's our starting basis. So we have the gamma no wind, the still air conditioned flight path angle, and if you have a tailwind, your flight path angle is going to be shallower, and if you have a headwind, your flight path angle is going to be larger. And so this is what you have to take into account, that when you have a headwind, you will descend with a much larger, steeper flight path angle. And before we move on, I'd like to spend a few words talking about what this flight path angle means to you as pilots, practically speaking. Like, how can you judge your flight path angle? So the way that you can actually judge it is, you have basically, you know, from a sideways drawing, here's, you know, a given field, and here's the runway on this field. And it has certain distances. And you're starting your descent, let's say, from the same point every time. Again, so you're at this point. And in, let's say, a still air condition, you're used to seeing the runway, you know, at a given angle. You know, let's say like this. So you're seeing the runway like this. And what your eyes are looking for essentially is two things. When they look at the runway, the shape of the runway, your eyes are basically looking for this height. So this is the still air condition. And they're looking for this height, you know, this width, basically. And most importantly, well, not even this width. Well, of course, you know, they're going to be looking at the width of the runway and on both sides, but actually what they're looking for is these angles right here. This alpha angle, like still air SA, like still air. Okay. And what happens, like this is the still air condition, still air. So what happens when you open the flaps, for example? Well, or, you know, let's say still air and clean configuration. Let's look at the first example where you're gonna have like still air and no configuration, or headwind and clean configuration. So if you have a headwind, you know, your flight path angle is gonna be steeper. So, and this would be headwind clean config. So what happens when you begin to see the runway from a shallower angle or a steeper angle? Well, you can imagine from perspective that essentially you're going to see the runway something like this little sketch over here. Of course, you know, it's a bit exaggeration, but this is what sort of happens, right? So it just became longer and you know, less wide. And these angles right here, and the eye is most usually working by these angles rather than the width of the runway. So you're gonna have a height in headwind, and the angles, you know, became larger. These angles became larger. Right. So in a headwind, the optimum flight path angle, you know, from a different place, and of course, you would need to alter your flight path essentially, you know, to, if you have a headwind condition, to this place, and basically looking down from this position. So if you're looking from this position, you're going to see the runway at a much steeper angle, right? And it might feel, under normal circumstances, when you're on this flight path, and this is supposed to be an eye from a sideways drawing, when you're seeing this. And under normal circumstances, in still air conditions, you know that if you see the runway at such an angle, you're going to be high, right? Because at this point, with the normal flight path angle, if you think about it, at this point, if you see the runway at this angle and your flight path angle is essentially, you know, the stair with the same with the still air condition, you're going to be long. However, because you have a headwind, you need to see the runway from a much steeper angle, and exactly because your flight path angle is larger. And this is what it means when the flight path angle is larger from a practical point of view, from piloting point of view, is that you see the runway and everything else in the surrounding by a larger angle, right? So you see it from a higher angle, it's going to be much longer and much less wide, for example, if we're talking about the runway. And this would be the correct side if you have a strong headwind. It might look that it's going to be long initially if your eye is used to the normal still air or light headwind condition. A strong headwind might seem that it's going to be long, but actually if you want to maintain like the same angle right here from this position, you're actually going to, if you want to see the same angle with a headwind, essentially you're going to be short, right? You're going to be short and you're not going to reach the runway. And so what happens if you have, on the other case, or on the other side from this point, if you experience a tailwind? Well, if you experience a tailwind, if you're looking at the normal angle, you're going to be long. So essentially, you need to move your entire flight path, back, so to speak, and to see the runway from a much shallower angle. And you need to see the runway from a much shallower angle. And of course, we're exaggerating here by a large amount, but this is just so that we understand the difference. So this is what you need to be seeing if you were to be landing in a tailwind. Well, of course, we're not going to be landing in tailwind, but just as a hypothetical discussion to make the idea complete, right? So this is what you would be seeing. And essentially what your eye sees right here is that, this height has greatly, so this was the headwind scenario, and this is going to be the tailwind scenario. And essentially, this height has reduced quite significantly, and these angles have, these are tailwinds. This is tailwind. So these angles have reduced as well. Right, and so this is what different flight path angles mean from practical piloting point of view. And you would have the same effect when you would open the flaps. I'll actually do another drawing because this has gotten quite congested. So here we are, just like in the previous scenario. Here we have the runway, and we notice from a given altitude, which is, let's say, up here, that from this point, we're gonna be long, right? So then after a given while, we open the flaps. So essentially, with the increase of the flight path angle, because, again, here we're going to have the two angles. So here we have the clean configuration flight path angle, and here we're going to have the flaps, the angle with the flap. And so essentially what you see with the clean configuration, let's say, is a runway which looks like this. All right, so it's very similar to the still air condition, let's say, for this instance. So you see a fairly normal looking runway, and you have these distances right here, right? So you have the height of the runway in clean configuration, and you have these angles which your brain sees in clean configuration as well. Right, so when you open the flaps, your flight path angle increases. So what you're gonna see the runway again from a steeper angle. And this is gonna be like smaller, essentially, and this is gonna be smaller as well. And here you have the runway. So you're gonna be seeing the runway when you open the flaps from a steeper angle than you originally did with the clean configuration. All right, so the height has increased. So this right here, so this was the flap, So it has increased, and these angles have increased as well. So of course you're not going to be remembering these all of the details, you know, when you're and you're not necessarily taking them into account when you're flying an aircraft, but just be aware that, you know, this is sort of the image, for example, during a landing by which your brain is working, right? So these are the sort of angles it sees, and this is how it sort of encodes what or decodes what you need to do. And again, this is sort of a more practical discussion of sort of what's happening, how you can understand flight path angle, because of course we discuss all these parameters and these influencing factors, how they affect the flight path angle. So for example, configuration and the wind, so that you understand that when you fly the airplane, right? So understand that when you have a headwind, you're going to have a steeper, larger flight path angle, so you need to be seeing the runway from a steeper angle, and so that you don't necessarily always come short when you have a larger headwind. Or for example, don't be freaked out when you extend the flaps and the airplane's nose is pointed lower towards the ground or closer towards the ground. This is very common with students, that, you know, it seems unnatural that the aircraft's nose is pointing lower during an approach when you extend the flaps. Well, you know, the aircraft's nose needs to point lower, and that's because of this effect right here, right? Because the flight path angle has to be larger than in case of the flap, in case of the configuration one, compared to the scenario when you use clean configuration, right? And you're gonna see a difference between the two scenarios. So when you extend the flaps compared to the situation when you're approaching with clean configuration, and this is quite normal. This is how the flight path angle sort of works in the practical sense of way, right? So I think we're done with the flight path angle and with the range, and we're talking about that. And let's talk just very, very briefly about endurance in case of the glide. So gliding for endurance. So when we're talking about gliding for endurance, we want to spend the most time in the air, right? And when you want to spend the most time in the air, what you want to minimize is the rate of descent. So you want your rate of descent to be minimal, right? So the rate of descent, as you remember from the previous videos, in the general case would be the power required minus the power available over with the weight. But of course, since the thrust is zero, and since the power available is the thrust times the velocity, in that case it's going to mean that the power available is going to be essentially zero as well. So how that modifies the whole equation is that the rate of descent during a glide is going to basically equal the power required over the weight, right? And for a given mass, of course, this is going to mean if the weight is, or the mass is constant, how we can influence the endurance, how we can optimize this, is we're going to say that the rate of descent is going to be minimal where the power required is going to be minimal. And I think that makes sense for like all of the aeroplanes. And again, we're not going to discuss here the jet and the propeller driven aircraft, because from the glide's perspective, you know, it's essentially all the same. Like if you have an engine failure, all airplanes are essentially gliders. So here you have the power and the true airspeed, and here we're going to have the power required curve. And I think it's very easy to see how the power required is going to be affected, or is going to be minimum at the VMP, right? Because this is where the power required is minimum. So essentially, it's that simple, that the best endurance during glide is going to be given by the achieved at the VMP. Right, and essentially the endurance is going to be affected in the same way as the range was, right? So essentially it's going to decrease if you increase the configuration. So if you have flaps, of course you're going to have much less time that you can spend in the air. And here comes the question, usually, like, what's the difference between endurance and range, basically? Let's look at quickly at an example. Like here we have the, well, let's try and draw it more straight. Here we have the ground level, and let's say here we have the runway. Right, and we're starting from the same altitude with both aircraft. So we're starting from right here. And, you know, we have our little glider right here. It could have been nicer. Okay. So what happens if we're gliding with VMD? Okay, so if we're gliding with VMD, and let's say that we're going to be gliding for a given amount of, you know, time, for a T amount of time. Okay, so for gliding with VMD, what you achieve is the minimum angle of descent, right? So this flight path angle is going to be minimal. And essentially, you know, so we're flying with VMD here. Okay, and you're gonna have like a given like rate of descent with, you know, VMD. And let's say that you reach the ground during this T amount of time, right? So in this T amount of time, we have reached the ground. And so we have the second scenario where you're descending with VMP. Okay, so what happens when you're traveling, or so we already know that the VMP is of course less than VMD, right? Because VMD is 1.32 times VMP, so therefore VMD is larger than VMP. So what happens if you travel or you fly with a slower speed than VMD? Of course, your flight path angle is going to increase. So therefore, the flight path angle is larger than it was for the VMD, right? But essentially, your rate of descent with VMP is gonna be less. So in the same amount of time, you're going to maybe, let's say, only get this far, right? So in the same amount of time, because you had a lesser rate of descent, you're still flying while the other aircraft has landed. And so this is what it means that you have more endurance, because you still have, within the remaining amount of time, you know, a given amount of time to reach the ground in this case. So the same vertical distance, so this Z, right? However, your flight path angle is larger than it is for the optimum scenario. So altogether, your range with VMP, so X minimum VMP, or let's say X best endurance BE, is going to be less than the range for the best range. Of course, you know, by definition. So if you're flying with any other speed than, you know, the best range speed, your range is going to decrease. But I think this drawing sort of sums it up quite nicely, that's the difference between the two. So in a given amount of time, you're gonna, you know, descend more with the VMD, but essentially your flight path angle will be, you know, as shallow as possible. So therefore, you're going to reach the furthest distance that you can. While on the other hand, if you fly with the VMP, you're going to have a smaller rate of descent. However, your angle is going to be, your flight path angle is going to be larger at the same time. And essentially, it's going to mean that you're, by the same time the other airplane has covered, Z distance, you're only covering, like ZV and D, or Z1, let's say, Z1 distance, you're only covered Z0, right, which is essentially less than this distance, vertical distance, but your range is essentially going to be less as well. And so this is why if you have an emergency with a powered airplane, and in most cases, with a glider as well, you would be flying around the VMD, to get the best range possible. Of course, we're not talking about glider strategy where you would be flying with a much faster speed to get, during a competition, for example, to get faster at the cloud base of another cloud to use it for thermaling. That's a different story. We're just simply talking about, you could say like gliding in an atmospheric model with no thermals, which is very sad for gliders, but I think this is what we're talking about. Okay, so that's it. The question of one more thing about the endurance, like how does wind, so the effect of wind on endurance. So because it's we presume the wind to be a horizontal motion of air, because it doesn't affect the rate of descent. So essentially, wind has no effect on endurance. Okay. So that's it for today's video. I hope you guys enjoyed it, and I hope it was informative. So we're going to continue in the next video with the landing. So thank you for your attention if you watched it this far, and I'll be seeing you guys in the next video.